Yeah, still loading. All right. Okay, so we'll be doing chapter 14 today. Chapter 14, there are 3 exercises. So I'm just going to look at one exercise today, which is the 2 questions. So it's just a very short class. Okay, so today we're just going to do a very short class. And before we begin the class, let us look at the equation. First law of thermodynamic. First law of thermodynamic, basically that is all it's about in chapter 14. Okay, we're just going to focus on this one equations. Delta U equals to Q minus Q. Okay, it should be a Q minus W. Now, this equations is very important, all right, because all of the questions in this chapter, basically they are going to resolve around these equations. We are going to just use these equations to solve most of the questions. And one thing that I wanted to take notes is that the negative in these equations, the minus sign in these equations is a part of the equation. It doesn't carry any actual meanings, okay? So in this chapter, like I told you before in the lecture, sign convention is very important. Why? Because by looking at the sign convention, you should be able to tell what happens to the heat, what happens to the work done, and also what happens to the energy, internal energy. Now let us begin with heat. Okay, so if you look at heat, now if you have a negative sign, okay, or now let us begin with positive. Now if you have a positive sign, what does it mean? It means heat is being added. Okay, heat is added to the system. Now what does it mean by system? System, now you have a container. Inside the container, it comes with a gas molecule. So the gas molecule together with the container, we treat it as one whole system. So if heat is being added into the system, then we use positive sign in our Q. If heat is being released, okay, if heat is a release or remove, okay, then we use negative sign. Okay, it's release or remove, then we use negative sign. So negative for the heat is being taken out from the object, from the system, and a positive heat means it is being added into the system. So Q is quite simple. Now let us look at W. W is slightly more complicated because you have to look at the terms, okay, the terms given. So if you have a positive W, okay, now if you have a positive W, then what does it mean? It means the work is done by the system. Okay, by the system. So for example, now let's assume you have a ping pong ball. Okay, kamu ada bola ping pong yang kemek. All right, so now you accidentally press a ping pong ball. So now the shape changes. It has it goes a bit inside on one side of the ping pong ball. So what happens now? If you heat it up, if you heat up this ball, and then the ball will expand. Okay, you heat it, you put it in the hot water, or if you heat it up, then it expands. So when it expands, this one we say the work is done by the system. Why? Because now it's the gas molecule inside the ping pong ball that is pushing the ping pong ball out. Okay, that is pushing the shape, the ping pong ball, the surface, so that it goes back to the original shape. So kamu punya ping pong ball sudah kemek sebab kamu tertekan dia atau terpijak dia kadangkala. So bila kamu letakkan dia dalam air panas, kamu panaskan dia sedikit dengan udara panas. Okay, udara di dalam dia akan tolak bola dia kembali kepada bentuk asal. That one we say that is the work done by the system because it is being done by the gas molecule inside the container, inside the ball. And then how about work done on the system? So if you have a negative sign, okay, if you have on the system, work done on the system, we use negative sign. Now what does it mean by on the system? For instance, if you press the ping pong ball, okay, you press it, you change the shape. Then we say that is the work done on the system. You are the one that doing the works, okay, not the gas inside the container, not the molecule inside the container. So in that case, we say the work is done on the system. Okay, so usually we'll look at it in terms of a compress. So if you compress it, then we do the works on the system. But if it expands, if the container, if the object move is because it is being pushed by the gas inside the container, then we say the work done by the system. And be careful here, because the negative sign has nothing to do, the negative sign in the equation, it has nothing to do with by the system or on the system. Okay, So it is part of the equation. So in case if you have a negative work done, then you need to use these equations and then you substitute with a negative value. So it becomes minus a negative value in case you have the work done on the system. And then one more thing that is not being stated in your books, which is the sign conventions for delta U. Now, delta U, how to determine the sign convention? Then you have to look at the equations for U. In chapter 13, we learned that U is equals to F over 2 NKT, in which it means if you're looking at delta U, then it means U final minus U initial. So if you expand the equations, then we will write it as F over 2 NKT final minus F over 2 NKT initial. Now, if you look at this equation, F, for instance, they are constant, okay? They have the same. It doesn't matter whether you're looking at initial state or the final state. Why? Because you're still looking at the same type of gas in the container. You're not changing the gas inside the container. You have this container, inside is filled with, let's say, you're filling with oxygen, O2. So if you heat it up, well, it is still O2 inside the container. Therefore, F is the same. Okay, because you're looking at the same type of the gas, you're not changing the gas inside the container. So F is fixed. In terms of N, it is also fixed. Why? Because what you're doing in this chapter, when it comes to the first law of thermodynamics, you're actually playing with the pressure, you're actually playing with the volume, and you're actually playing with just the temperature. These three things, which means you didn't change the mass of the gas in the container. You're looking at the same system. You're not adding more molecule inside it. Okay, so it has the same amount of molecule. It has the same type of gas. Therefore, degree of freedom is constant and is constant before and after you heat up the system, before and after it undergoes a thermodynamic process. And then K obviously is a constant because it's known as Boltzmann constant, which means this equation can actually be simplified and be written as F over 2 NK T final minus T initial, which is your delta T. Okay, and this part, it shows you that delta U depends on temperature. Okay, delta U depends on temperature. In another words, if you have a final temperature, if final temperature is larger than initial temperature, if your T final is greater than T initial, then you will have positive internal energy, right? If your T final is less than T initial, then you will have negative internal energy. And in another words, if you have a T final, which is equal to T initial, which means your object undergoes isothermal process, then the delta U is equal to 0. Okay, delta U is equal to 0. So that is how we determine whether it is a positive or a negative value. Where internal energy, the change in internal energy, delta U, it depends on what happens to the temperature. Now, don't get confused between temperature and heat energy. Okay, energy could be increased even if you remove the heat from the object. Okay, even if the heat is being released. Why? Because there is work done in the equation. So it depends on all three variables. All right. So sometimes you might have positive internal energy, but you will have negative Q. Okay, it doesn't mean that when temperature increase, definitely you will have more heat energy. No, not necessary. It depends on the work done as well. Alright, so dia tak semestinya kalau kamu punya temperature increase, heat energy mesti increase. Dia tak sama macam kamu punya chapter 12. Okay, chapter 12, if you increase the heat, if you increase the temperature, then the heat energy will increase. That is what happened in chapter 12. But when it comes to chapter 14, okay, that is not the only things that we're looking at, because there's another two variable that could affect our equation, which is the pressure and also the volume. All right. So all three things, when you add them together, when you look at all three at the same time or at once, okay, then you might have a situation where temperature increase, but then heat energy is being removed from the system. That could happen, right? That could happen. That is because of the work done, because of W in our equations. So it depends on all three variables. So you cannot make a simple conclusion based on what happens to the temperature. No, okay, no. So we have delta U, Q, and W, where you have to know how to determine its sign convention. Question won't tell you the sign convention. Question will just tell you heat is being added or removed. Question will just tell you whether the work is done by the system or on the system. Okay, and sometimes questions will just tell you now you increase the temperature or you decrease the temperature of the system. All right, but it won't tell you directly that you have a negative value. Okay, it will just give you a value. You yourself gonna determine whether it is positive or negative. So that is equations. And then we have another ways that can be used to determine the values of delta U and W, which is based on the P against V graph. Okay, based on P against V graph. Now let's look at the graph. So if you have a P against V graph, right, P against V. So for example, you have a isothermal process. Now, isothermal process, okay, is a temperature constant. Okay, that is what we know. Okay, so what happens here? In order to calculate the delta U, you're just going to look at initial and final state. Okay, let's say this is your initial, this is your final. So delta U, it depends on, okay, depends on just the initial and final state. It doesn't matter how you proceed, how you move, how you change the gas from initial state to its final state. It could be undergoes isothermal process. Okay, it could be undergoes isobaric process and then isovolumetric process. It could be. Okay, it doesn't matter. What we are looking at right now is just the final and initial state. You're just looking at the final temperature and initial temperature. In other words, we say that delta U, it does not depends on the process. Okay, or we say it does not depends on the path taken. So you can straight away move the gas, change the gas from initial state to final state through an isothermal process. You can let it undergo isobaric and then undergoes isovolumetric to reach a final state. Also can, it doesn't matter. What you're going to look at is just final temperature and initial temperature, your T final and your T initial. That's it. That is what we care in internal energy. But when it comes to work done, okay, when it comes to work done, W is area under the graph, okay, under the graph. So in other words, it depends on path taken. Okay, it depends on path taken. So if you take an isothermal process, then the path taken is just right here. This is the path taken. This is the area under the graph. But if you're looking at isobaric, okay, isobaric, then isovolumetric, then the work done would be much more greater than the isothermal process. Why? Because now it has a larger surface area. So W depends on area under the graph, whereas delta U, it depends just on the initial and the final point. So that is all we care in our equation. That is how we check our equations, how we obtain the value for our equations. Okay, so basically in this chapter, we're just going to focus on how to use this equation. Delta U equals to Q minus W. Okay, so now we are done with the summary for exercise 1. For thermal process, processes, we are going to look at it in the following section. Okay, I will go through isothermal process, isobaric, isovolumetric, and also adiabatic process with you guys in the next section when we have a 2-hour slot. So today we're just going to focus on exercise 1. We're just going to look at how to apply these equations. So exercise 1, a force acts on a gas compressing it, and it does 25 joule of work on it. So if you look at this equation, now work is being done on the gas, which tells you that this value, this 25 joule, is a negative value. Okay, because now you're looking at work done on the system, work done on the gas. The gas is then cooled so that it loses 15 joules of heat energy. Heat loss means that it is being removed from the system. Okay, it is being removed from the system. So if it's being removed from the system, then once again, this heat energy, the Q, is a negative value. So based on these two statements, I know that W equals to negative 25 joule, and then my Q equals to negative 15 joule. This is based on the statement given. Work done on the system. Okay, this is based on work done on the system, and then energy is being removed. Okay, is a loss. Okay, it loses energy. So okay, loses energy means remove. Loses heat energy, so it is being removed. So therefore, you have a two negative value right here. So now you want to find the change in internal energy. So delta U equals to Q minus W. So like I told you, this minus sign is part of the equation. It has nothing to do with whether work is done on the system or by the system. All right, so be careful. So it is equals to negative 15 minus negative 25. Therefore, delta U is equals to positive 10 joule. Does it make sense? Yes. Okay, does it make sense? Yes. Okay, so you have a negative 15 minus negative 25. All right. So this is the values that we have. All right, this is the values that we have. Okay, so now you have a 10 joules. Okay, 10 joules of a change in internal energy. So now I give you a few minutes to write it down. Okay, including the summary lah. All right, including the summary. So you write it down. Record it, write it down. Oke, bagian beberapa menit, and then kita tengok soalan 2, lepas itu kita tengok skip process, and then after that I will let you guys off. Okay, so if there's anything that you don't understand, you feel you got confused, okay, make sure to ask, right? Because we are going to apply these equations again in the following subtopic, right? So chapter ini memang dia semua main dengan satu equation sahaja, delta U equals to Q minus W. So kalau anda tak faham part ini, anda kena tanya sekarang. Kalau tak tanya sekarang, nanti dia akan jadi susah. Okay, lagi 2 minit lah bagi anda catat. So kalau dah okay, then we will try the questions 2. Okay, we'll try questions 2. We will see why. Okay. Right? Okay, question 2. Questions 2, I think they accidentally gave you the answer already. Okay, never mind. We will go through it and see why. Okay, not just by looking at the final answer, but we must understand why. Okay, why something happened. How did it happen? So a gas expands under constant temperature condition. Now, the key words right here is constant temperature. So like I told you just now, delta U, it depends on the temperature. If you have constant temperature, then delta U is equals to 0. Okay, delta U is equals to 0. So, and it does 30 joules of work against surrounding. So it does the works, it do the work. Work is done by the system. So this phrase, it tells you it is by the system. Okay, the gas is doing the work. So what is the change in internal energy of the gas? So since T is constant, U is also equals to constant, means that the final and the initial internal energy is the same. Therefore, change in internal energy, delta U, is equals to 0, right? So this is why it happened, because of the equation Fn equals to nkt. Because of this equation, delta U equals to F over 2 nk delta T. So when something is constant, okay, then it means that delta is equals to 0. So if this equals to 0, then delta U is also equals to 0. So find the amounts of heat energy absorbed or lost by the gas. So now according to the questions, we have delta U equals to 0. And according to the questions, we have W equals to positive 30 joule. Why? Because it says now the gas is doing the works. So it is the work done by the system. So work done by the system, it is a positive work done. Therefore, by applying the equations delta U equals to a Q plus W, you obtain Q equals to 30 joule. Okay, 30 joule. So that is how you solve the questions. You look at the questions, you try to identify the keywords. All these keywords, it comes with hidden meaning. Okay, it comes with hidden information. All right, so now I give you 2 minutes to write it down, especially questions A, and then we will discuss the next questions. Okay, we will go through the summary in the next subtopic. Okay, yeah. Right. So we are done with the first subtopic, okay, which will focus a lot on the equations. Now let's look at the second subtopic. Okay, let us look at the second subtopic. So second subtopic is the thermodynamic processes. Okay, so we're just going to go through the summary today. Okay, go through the summary today. So thermodynamic processes, we have 4 processes. The first one, let us begin with isothermal. Okay, isothermal. So isothermal process, if you look at this term itself, now it has the word thermal right here. Okay, so thermal, it means the temperature. Therefore, this one, it tells you now you have constant temperature. Okay, so this is the keyword. This is the ways that I use to memorize which variable is constant. So by looking at the word thermal, I know this one, it has a constant T. So when T is constant, then what happened? It tells you P depends on V, or V changes with P. Okay, so according to Boyle's law, okay, now when we have a constant temperature case and we want to investigate the relationship between P and V, we look at Boyle's law. Okay, we look at Boyle's law. So according to Boyle's law, what we have right now is P is inversely proportional to V. Okay, Boyle's law tells us the relationship between P and V. When you have a gas in an ideal system, in a closed system, and then when you rearrange these equations, you obtain PV equals to a constant value. So this is what we have based on the information, based on the conditions given, constant temperature. So from the first constant temperature, other than it tells you the relationship between P and V, other than we can use it to investigate relationship P and V, we can also deduce the values of delta U based on this statement, constant temperature. So if T is constant, then delta U is equals to 0. Okay, delta U is equals to 0. This is the information that we can get. And again, I would call it hidden information, because question 1 tells you now the internal energy, the change in the internal energy is 0. It will just tells you now your object, this system, the gas, it undergoes isothermal process. So when you have the phrase isothermal, for instance, you have to know delta U is equals to 0. Okay, delta U is equals to 0. And when delta U is equals to 0, by applying delta U equals to Q minus W, we then obtain Q is equal to W. So they are all connected, you see, they are all linked to each other. And then, well, since we say W is equal to Q, how to determine the value for W? Then we have to look at the graph. So if you look at this relationship, P is inversely proportional to V, then the graph will look like, okay, now this is your P against V graph. So if they are inversely proportional to each other, then you obtain a graph look like this. So this is the graph, and from here you then derive the equation for work done. Okay, you can then use it to derive the equation for work done. And since you have a curved graph, okay, if you complete the derivation, I'm not going to show you the derivations again here because I've already mentioned it in your lecture. So if you combine the graph and also these equations together, you will then see that W is actually equals to nRT and then ln V2 over V1. Okay, or it can also be written as W equals to nRT ln P1 over P2. Why? Because of the equations on the Boyle's law, okay, the equation from Boyle's law. So this equation, Boyle's law also tells us that P1 V1 equals to P2 V2. If you rearrange the equations, V2 over V1 is actually equals to P1 over P2. So you see, they are all related. Okay, they are all related. So you cannot look at them one by one. You have to look at them as a whole. So from isothermal, we know that temperature is constant. When temperature is constant, we know delta U is equal to 0 and that W equals to Q. And when temperature is constant, we know that P changes with V. And the law that shows us the relationship between P and V is Boyle's law. So from Boyle's law, we then obtain the equation PV equals to constant. All right, we then obtain PV equals to constant. So they are all related. Okay, they are all related. So now let us look at the second types of the process, which is the isovolumetric. So isovolumetric. Well, if you look at isovolumetric, once again, the phrase itself, it gives you volume. So which means it tells you now you have a situations where volume is constant. Okay, where volume is constant. So if volume is constant and you want to investigate the relationship between temperature and pressure, then we are going to apply Gay-Lussac's law. Okay, Gay-Lussac's law. Or it has another name known as pressure law. Okay, so it has two names. So based on this Gay-Lussac's law, we obtain the relationship between the pressure and temperature, where pressure and temperature, they are directly proportional to each other, and that when you use P divided by T, it is equal to a constant value. Okay, it is equal to a constant value. Then how about the graph? Okay, how about the graph? Now we want to sketch the graph for this Gay-Lussac's law. So if you look at the graph, now we have P is directly proportional to T. Okay, and we want to plot the graph of P against V. According to the informations given, now our V is constant. If V is constant, then basically it's just a straight line graph. Why? Because this straight line graph will give you the value of V, okay, just one V, which shows you V is now constant. Okay, the initial state and the final state, they both have the same volume. And again, this graph, it shows you P is directly proportional to temperature. P is directly proportional to temperature. When temperature increase, your pressure also increase. Okay, so when your P increase, T also increase. Okay, because they are directly proportional to each other. So this graph, it gave you quite a lot of information. Then how about our equations then? So if you look at the equations of delta U equals to Q minus W, well, we know that W is area under the graph. Okay, area under the graph. If you look at this graph, does it have any area under it? No, right? So in this case, we have W equals to 0. and that therefore delta U is just equals to Q. Okay, delta U is just equals to Q. So that is what we have based on the isovolumetric, the constant V situations given. Okay, the condition given. So that is the second example. Now let's look at the third process. Okay, that is the second process. Now let's look at the third process. Third process, we have isobaric. Okay, isobaric process. So isobaric process, now if you know what does it mean by barometer, it is an equipment that we use to measure the pressure. Then this one, it tells you, okay, isobaric, barometer, baric. So this one, it tells you, now you have a situations where the temperature, the pressure is constant. Okay, the pressure is constant. So when pressure is constant, okay, when pressure is constant, what are you going to do? You want to investigate the relationship between T and V. The law that we use to investigate to show the relationship between P and V is our Charles' law. Okay, it's Charles' law. So Charles' law tells us that T and V, temperature and volume, they are directly proportional to each other. And that when you use V divided by T, it is equals to a constant value. Okay, it is equals to a constant value. So now let's see. Okay, let's see if we have the right graph. Okay, how to sketch the graph. So based on this relationship, now again, T is directly proportional to V, but what we want is a P against V graph, right? P against V graph. So we cannot plot a graph for T against V. We're going to plot a graph of P against V. Okay, so temperature, we'll leave it first. How about P against V? If you look at the condition, it tells you constant pressure. Constant pressure means that the pressure at the initial state is equals to the pressure at the final state, in which it means you will have a horizontal line. Why? Because horizontal line is the only situations that can give you just one P, one pressure. Okay, one pressure. So in this case, we have P and V. Okay, P against V, where P is a horizontal line. Okay, where the process is a horizontal line. Isobaric, it's just a horizontal line. Okay, now let us go back to the equations again. So when you have a constant P, delta U again is equals to Q minus W. If you look at the graph given, now my W is no longer equals to 0. My delta U is also not equals to 0 because now my P is not constant. My temperature is not constant. So what am I going to do? I look at the graph. Area under the graph is very simple. Now you have a rectangular shape where P is a fixed value. Therefore, area is equals to P times delta V. Okay, the changes in V, the final V minus initial V. So this is your V final, let's say, and this is your V initial, for example. So area equals to P times delta V. Therefore, these equations can then be written as delta U equals to Q minus P delta V, right? So this is how you expand the equation. So now that you have all of the items, you can then proceed to calculations. All right, so we have the equations already. So you have to be careful with the work done. Okay, work done. So area is equals to P over V. Therefore, your equations can be written as delta U equals to Q minus P delta V. So it's very simple. The last one, okay, last one is a special case, a diabetic. Okay, a diabetic. So a diabetic is a very special case where nothing is constant. Okay, so all three variables, P, V, and T, they are all changes. Okay, they are all changes. P changes, V changes, T changes. So in that case, how are we going to do a calculations? So we have delta U equals to Q minus W. How are we going to use this equation? Well, if P, V, and T, they're all changes, but there's one more thing, okay, that we haven't looked at. When it comes to a diabetic, okay, when it comes to a diabetic, our heat is constant. The energy is constant. Okay, the Q is constant. So no heat is being transferred in and out. Okay, no heat is being transferred in and out. Therefore, we say, okay, now rather than constant, I would say Q is equals to 0. Okay, because no heat transfer. Okay, no heat transfer. That's why none of the value is constant. Okay, because there's no energy being transferred in or out. So if you change one of the variable, then the other two will change at the same time. None of them can be kept constant. Okay, none of them can be kept constant. Okay, so let's see. Okay, let's see what are we going to do. So now we have Q equals to negative W. Okay, Q equals to a negative W. So if you do these equations, if you rearrange the equations, yeah, wait, where's my equation just now? Okay, so basically you can use the equations from, wait, where is my equations? Delta U. Yeah, okay, so basically if you look at these equations, I now have delta U equals to negative W. All right, so delta U, what is the equations? Just now we have F over 2 NK delta T. Okay, it is equals to negative W. Therefore, W equals to negative F over 2 NK delta T. So if you want to expand this equation, now can you expand this equation? Obviously you can. Okay, obviously you can. But because of this negative sign, W is equals to F over 2 and K. Now instead of T final minus T initial, it is now T initial minus T final. All right, that is because of this negative sign. Because of this negative sign, now you use initial minus final. Okay, kamu darab negative sign ke dalam equations kamu, jadi bukan lagi final tolak initial, tetapi initial tolak final. Okay, now let's see how are we going to sketch the graph then if, okay, if your P, V, and T, they are all changes. Macam mana kita nak sketch graph? Untuk situasi di mana ketiga-tiga variables ini semua berubah. So in order to sketch a graph, again, I'm going to begin with P against V graph. Now, in order to show that the temperature changes, what you have to do, you need to do two dotted line. Okay, what do a dotted line? Where you have here temperature 1, here temperature 2. The one above is the one with the higher temperature. Okay, because like what we see just now, P is directly proportional to temperature. If temperature increase, if pressure increase, temperature increase, right? So therefore, the one lying above on top of the T2, okay, T1, it has a greater value compared to T2, right? So this is how you sketch a graph. So in a diabatic, you need to show T1 and T2, the curve for T1 and the curve for T2. Why? Because you need to show a line where it can show the reader there is a change in temperature. So how to prove that there is a change in temperature? You draw a line from T1 towards T2. Okay, you draw a line from T1 to T2. So it's moving from one temperature towards the other temperature. So the graph like this, it shows that there is a change in pressure, there is a change in volume, and also there is a change in temperature. In isothermal process, okay, we just shows one curved line. Okay, we only have one curved line in our graph. So this curved line, okay, this graph, it shows that we only have one temperature. Okay, one temperature. So don't get confused between the isothermal and also adiabatic. Even though the graph looks very similar, okay, there is a slight difference. So in isothermal, you have only one curved line. If you have only one curved line, then it means you have only one temperature. Okay, if you want to show that there's two temperature, then you need two dotted line. Dotted line for T1 and also dotted line for T2. Okay, dotted line for T1 and also dotted line for T2. So that is how we sketch the graph for a diabatic process. And also, that is how we calculate, this equation is how we calculate the work done in a diabatic process. Okay, basically it's by using the equations for internal energy. So we have learned how to calculate work done in all four processes. And we have seen how to sketch the graph, right? So basically that's all, okay? That's all that we have to know in chapter 14. All right, so I will give you some time to write it down. Write it in your own words so that you know what is going on. Okay, write it with your own words so that you know what is going on. So I think that marks the end for today's class. Okay, basically today's class, I'm just going to finish exercise 1, and I'm just going to explain these 4 processes to you. Once you know these 4 processes, then in our next lesson, we will finish exercise 2 and exercise 3. Altogether, I think there are 7 questions. Okay, I think there are 7 questions altogether. So today, you just write down the summary. If there's anything that you don't understand, make sure to ask. So in the following sections, we are going to go through just the exercise. No more summary after this. Okay, no more summary after this. We're just going to focus on the exercise.